Unmanned aerial vehicles, such as drones and quadcopters, rely heavily on GPS for navigating within an environment. Indoors, GPS is often diminished to the point of unusability, making indoor navigation difficult. We seek to identify and implement various systems which enable an unmanned aerial vehicle to navigate autonomously in GPS-deprived environments, such as indoors. Our team consists of 3 computer science seniors: Tanner Borneman, myself, Joseph Krusling, Matt Manley, and our advisor, Mahdi Naruzi. Unmanned aerial vehicles rely principally on GPS for localization, so GPS-deprived environments pose a major challenge. We seek to explore and implement various strategies for automating UAV flight without access to GPS. The first strategy entails the use of many fixed cameras placed within an environment, which identify the location of the UAV through the fusion and analysis of their individual camera feeds. The second strategy uses Wi-Fi signals obtained from numerous access points and analyzes the relative signal strengths to localize the UAV. These strategies will be used simultaneously to achieve robust localization. Here are some example user stories we've created for our project. Since our project focuses more on research and automation of a device, we don't necessarily have users, and our tasks don't always fit cleanly into user stories. By design, our system should require minimal user interaction. Here you can see the overall design diagram of our first non-GPS localization strategy, using a series of cameras positioned around a room to locate the drone. These cameras are constantly recording and submit a feed of the images to the backend server. The server runs an object detection algorithm on each feed to determine the location of the pixels that represent the drone in the image. The 3D position of the drone can then be geometrically approximated with this information, since the position and orientation of the cameras is known ahead of time. Our second strategy uses Wi-Fi signals for localization. The drone will use the received signal strength information from each access point to relate against a pre-scanned Wi-Fi map. This information should give the drone's position to about 3 meters of precision. This is usually enough to know if we are in a room or a hallway. Wi-Fi localization can also be used without a predefined map. Using simultaneous localization and mapping techniques, we can make the drone map the environment with Wi-Fi as it flies. This project entails a number of constraints. First, we must operate without the use of GPS, since our goal is to identify strategies for localizing a drone without a need for GPS. We need to ensure the safety of the general public while we research and develop these systems, so our testing will occur in a contained lab environment. Depending on the exact flight characteristics of our test drones, we may need to seek a license from the FAA to operate. In the beginning, we will only support a single model DJI drone to avoid the complexity of interfacing with a multitude of different devices. The majority of our computation will occur off the UAV, either on a PC on the ground or in the cloud. Reliable drone server connectivity is therefore required. Finally, we will focus our attention towards commercial, civilian, and rescue applications. We are still in the research and prototyping phase of our project. So far, we've developed a custom software solution which uses the DJI mobile SDK to transmit video to a central processing computer over a network. We're also prototyping our 2 localization strategies that we described earlier. We've developed some image processing code, which can rapidly identify the location of a drone in an image within a video feed. And we're experimenting with the Wi-Fi localization using the relative signal strengths of consumer routers. By the end of this semester, we expect to accomplish a full case study on both external camera and Wi-Fi localization. By the end of our project, we expect to have a system in place for controlling the drone with this localization data. After that, we will be able to allow the drone to navigate autonomously through hallways and rooms. Due to the exploratory nature of our project, we don't have a rigid timeline. However, we plan to have the 2 case studies on the fixed camera navigation and the Wi-Fi localization finished before Thanksgiving. When that's finished, we will reevaluate and develop a timeline for the rest of the project. During the early research phases of our project, we've chosen to each focus on specific areas. Currently, Tanner is focusing on non-optical localization using Wi-Fi signal strength and potentially other sources such as cell tower signal strength down the line. Joseph is focusing on UAV localization using optical means, specifically the strategy involving the numerous cameras placed in a room. Matt is focusing on the raw interactions with the DJI drone, such as researching how the API can be used to control the drone and how we can access the raw sensors that the drone comes equipped with. As time goes on and our project continues to develop, there will be considerably more overlap of our roles. Ultimately, all of these systems must interface together, so we are being considerate of how our individual parts will contribute to the whole design. For safety and legal reasons, we will likely only be able to present videos of the drone operating, and will not be able to perform a live demonstration. We plan to have examples of the drone navigating in an unfamiliar indoor environment, without the use of GPS.